And today I will show you a very, very introductory talks about a few principles on visualizing data and especially scientific data. First of all, what does it mean, visualizing? Visualizing means try to convey the idea or the meaning of a large amount of data by means of a graphic, okay? And by means, essentially, of an effective graphic. And what I present here is just a very quick tour about a few ideas on how to and how not to visualize graphs. Most of the material I show is due to the work of this guy, Mr. Edward Tufte, which devoted his own life to this kind of problem, and he wrote a few books that are milestone in scientific visualization. Okay, first of all, why we need graphics for visualizing data? Numbers probably may be enough. Why not? Take a look at this example. We have 4 sets of 11 points in the plane with x and y coordinates. Okay, so in the first column we have 11 points and then other 11 points and so on. Okay, what's nice about these points? That they share a lot of similar statistical property. They are the same number, the mean of x coordinate is the same, mean of y coordinate is the same, they have the same regression line, they have the same standard error, they have the same sum of squares, same regression sum of square, same correlation coefficient, same R squared. Okay? So pretty much they should be very, very similar, just looking at the numbers. Okay, this has been published in 1973. Okay, this is how they look like. Okay, they are very different, but you can catch their difference only if you plot them. Okay, this is a typical example where numbers here are not enough to convey the meaning of these points. Very well. A bit of history. Scientific visualization has probably its first attempt around year 1950, where this drawing has been found and is representing the orbits of a few elements in our solar systems. Okay. Then nothing else was found until probably 18th century, when this guy, Mr. William Playfair, started somehow the foundation of scientific visualization, enriching his reports, his economical report about the economy of Ireland and Great Britain with graphs like that. Nowadays, we moved to very, very complicated graphs now. This is a typical example in biology. It's circus examples, okay, representing data on chromosomes. And between this and this, we have 200 years of development of scientific visualization. Okay. What are the basic principles following the work of Mr. Tufte? A good graph should, first of all, show your data, okay, clearly. That's the meaning for why we are doing visualization. Focusing on the substance of the data rather than its methodology. Avoid distorting data, okay? Don't try to convey different meaning. try to devise an effective way to present many numbers in a small space. Try to push the reader or to help the reader in comparing different aspects of your data, revealing different level of details of the data, from a very zooming out to a very focused view, but essentially, above all, show the data. And by me, sorry, did I say show the data? Okay. This is always the most important fact. Very well. Let's show a few graphs that are not following these rules. And these graphs have been published. That's probably the most important fact about them. This graph has been published in a quite high-level biological journal. Exactly like that. So I wonder what the reviewer of the paper thought about it, but okay. So this is an empty graph showing a function of the frequencies of a function of allele in the chromosomes. I don't know what the author of the paper had in mind. Then we have this one. Same apply. Okay, they are showing same X and Y data twice with no description of what's on the axis. And the caption weren't helpful as well. Then we have this. This is not a wrong graph. They are displaying some data with reasonably X and Y scales, but what's the problem here? There's no labels on the axis, but then what? The 3D. What's the point of having a 3D here? Okay, just confusing people. What about this? What's the problem here? For instance, but here it's more subtle. Look at the Y scale. The difference between the first bar and the last bar looks like, let's say 8 times, but it's not like that. The Y scale starts from 2000, from 200, okay. So this is the way of combining the meaning, of suggesting the reader that the last data is way higher than the first one, while it's not like that, okay. Then this is a very typical example in a lot of publications the last 10 years. Networks, points connected by millions of lines, that now, network science, now they are called airball, okay, which I really wonder what meaning they convey, okay. It's art, probably, but nothing more than that, okay. I don't see any science here. There's useful science. And then moving from science to infographics, there are this kind of plots that are very famous in probably all newspapers around the world. What's the problem here? Here the problem is distortions, okay? Look at the first line. The first line here representing data in 78 correspond to a value of 18. Last data corresponding to a value of 27.5 looks way larger. But why? Only because there's the perspective fooling you. This is a much more reasonable display for the same data, okay? Where you see that the difference between the first and the last data has a very different ratio than here, okay? And same here. Here is the same problem like we have seen before. The 3D here also applied to not only the graph but to the axes themselves is only confusing. And then there's this one. This is has been defined the worst graphic ever to find its way into print, okay? Is displaying 5 numbers, okay, which is the attendance to a given US university divided by age group 25 and over, under 25, okay? So the sum of the both number for each given x point is the same, okay, because it's just the 100 minus the other. So why employing colors, 3D and whatever just to display this 5 points, okay? Okay, so now we move to another problem, which is pie charts, okay? Pie charts are so famous that they are everywhere, and they are one of the worst things you can think of in scientific visualization. Do you know why? Apart from being 3D, which is even worse, okay? Why pie charts are not a good way to represent data? Exactly, because the human eye cannot interpret circular rounded shapes in correct terms of ratio of areas. Okay? These two sectors have the same angle, the red sectors, but for everybody, the right one looks much larger than the left one. Okay? So if you want to fool your reader, use a pie chart and put the sector you want in the right position. And then you can get to things like that, okay? So apart from me that I'm colorblind, so this is a nightmare. But even for probably a normal human being, is not conveying much of a meaning, okay? And probably this is the only good pie chart. Okay. So far, I show you what you should not do. What should you do? A few simple rules. Try to create the simplest graph that convey the information you want. Okay? So, if you have to display a given number of information, you have to think very carefully which is the simplest way to do it. Focus on visualizing patterns or on visualizing details, but depending on what you want to highlight, okay? And be honest towards your reader. It's allowed not to start from 0 in the axis, but only if it's meaningful for what you want to show, okay? These are two examples where if you want to highlight the difference in a particular range, okay, you're allowed to start from 600, okay? But first you have to show, or you have to explicitly declare, so point the reader that you're doing this. Use a reasonable scale. Plot in linear scale what is meant to be plotted in linear, and plot in log only what is meaningful to plot in log. Otherwise, this is distorting data. If you have an XY plot with overlapping points, try to show how many points are overlapping using shadowing. Otherwise, you are not explicitly telling your reader how many points are in that cloud. If you have a line plot, for instance, of a phenomenon occurring a long time, don't connect dots with lines unless it's meaningful to do so. But if you have no reason to assume that between time 10 and time 18 there's a linear relationship, leave it alone, okay? Don't suggest the reader a flow in the process which is not existing or it is not supported by data. And if you have to display many lines, it's perfectly meaningful to aggregate them, but be careful what you're aggregating. Okay? And if your idea is to compare series of data that probably lives in different ranges and you have to compare their fluctuations, then you can modify axes reasonably, okay, meaningfully. And then, this is not for me, but use a reasonable set of colors to display reasonable ranges. If a range goes from 0 to 50, okay, you can choose a palette of increasing or decreasing darkness. But if you want to display a very different range, highlight that you are displaying a very different range using different colors as well. And then avoid what is called chart junk, okay? So mixing up the data with rubbish, okay? Which is now, this chart junk now goes under the name of infographic, okay? And remember what this architect in early 90s says, that ornament is a crime whenever you want to display something, okay? Okay, the most important principle you will have to stick in mind is that a good rule is always trying to maximize the ratio between the data you're displaying and the ink you need to put in your graph to display them. Let's start with this bar plot, okay? How can I maximize my ratio? Well, I don't need the grid, okay? Why do I have to put all this gray in the background? Okay, why do I have to put the part of axis on the other side? I can get rid of the y-axis if I put some negative little dots, little lines, and then I can also get rid of all the rest of things. Okay, this is probably the most effective way of displaying the first set of the data set I showed before. This is, you do know this chart? They are called spark lines, and they are probably the best example of a graph that maximizes the data shown and respect to the ink you need to use. Very well. I conclude with a couple of examples. This has been defined the best graphs ever shown. It's a graph, very old, which is conveying a lot of information about Napoleon's Russian campaign. There are a few lines, okay? There's a temporal axis running on the x, and you have a few flows representing the size of the army, the geographical coordinates, the direction the army was traveling, the temporal location, the weather temperature. Okay, this is a very effective way to convey a lot of information in a very, very nice piece of scientific visualization. And I'll leave you with this kind of infographic that I found, and I abstain from comment. Thank you very much. Yep.
Use the microphone.
I have a question about when to use bar plots or when to use just points. Is there any?
If you just, I mean, bar plot is showing. Bar plot tend to show you the idea of an area. Okay, whenever it's meaningful to consider also an area under a point, a quantity. It's better to use a bar plot. But if our coordinates just one point, just a scatter plot could do it. However, that's just a stylistical thing. It does not a real difference because pretty much they are conveying the same information. On the point of view of maximizing the ratio, clearly 1 point. If a point can do it, use 1 point.
Sorry, a question back on pie chart. Usually, I think to pie chart when I have to represent some data that are not important the relation between two different data, but between the total and the data, and usually without 3D and putting in order decreasing to explain what is bigger and what's not. Do you think it's a bad approach or not?
The problem is where you put your sector sometimes. Okay, so if you want to use your pie chart, be careful that you don't highlight sectors that doesn't need to be highlighted that much. Okay, put them in a position that are not fooling the eyes of the reader. A typical example of this kind of data is metagenomic, where all the set of data are we're called compositional data, so they are sum to 100 or like. And in metagenomic, no one is using pie chart. They are always bar plot with a fixed length.
Hello, can you hear me? Yep. I'll talk loudly. You put up a picture earlier with lots of points, with lots of lines between them, and you said it looks like art. But actually, if you do have lots of objects and you want to show relationships where there is one relationship to every other one, big or small relationship, what is a good way to do that? And just to finish, this is a problem I'm facing, and the only thing I can think of is to use force-directed graphs to bring strongly related points, but that's still not a very good image.
Well, this is a very important problem in visualization in network theory. And in fact, given a network, so a set of points connected by line that you want to represent, there are at least 100 different layouts that can help you visualizing your data. And for instance, using force-driven, it's one of the examples. As far as I'm concerned, usually the strategy I use is first to focus on communities, so groups of points that are more connected, and then first I like them, and then if you need to highlight something different, then focus on specific part of the network. So first display an overall plot well separating well-connected and less well-connected part, and then focus on the different elements. And you can do it using very different layout, and somehow, I mean, one layout is better than another, also for the kind of things you want to display. If you also have to add weight or width of the lines connected, that could be a problem. So you have to. One of the things we are doing, for instance, when you plot a correlation plot, things like that, you just plot the correlation over a given threshold, warning the reader that all the correlation lower than a given threshold are not displaying, for instance. And then you can focus on a zone where you can display all the connection, but not on the overall graph.
Would you recommend to, I'm a beginner user of Python, less than beginner. Would you recommend to try to use Python to create your marvelous graph, or some other, let's say R?
I have two observations. The one is that I would have expected more bashing against scatter plots. So you've shown a nice case in which you have like 20 data points, and that kind of works because you put some opacity to, I don't know, 0.4, it works. But I think 90% of the times I see scatter plots, they're totally useless because you have hundreds of points, and then either you put alpha very low, and you lose part of the data, or you put it so high that, again, so 90% of the times I see scatter plots, I would like to see hex bins, for instance.
That could be a solution.
And I think we have more and more data, so more and more scatter plots are useless. The other, this is just an observation. I'm quite neutral on the story, but Seaborn is being publicized quite a bit, and it goes quite a bit against the rule of minimizing ink ratio because it puts colors. And well, I never thought seriously about it, but plots look nice to me. Maybe, I don't know, I'm just biased by junk charts, but that really goes in the direction of putting grids, putting colors, background colors.
I think that, I mean, some of the things that Edward Tufte said in his book are a bit provocative, okay, just to avoid this plethora of very bad graphs. There's no free lunch theorem. There's no solution that works for every situation. Okay, so clearly every situation can be, even it's depends also to the community you are directing your information. Okay, whether are just hard scientists or general public or intermediate. So and you have to adapt also your visualization to the people you are directing to. But I agree with you that you have always to consider what is your particular situation. These are very general rules that are not wrong, but cannot be taken for granted for any situation. They are on the web, on my website.
I have one last question. With the rising of tools like D3, GS, and Bokeh, somebody started to asking about interactive visualization is always better than static visualization. I mean, the interactive where the user can pan, zoom, and search for his data.
Again, there's no general rule. You are, for instance, try to help the reader in deciding or tuning parameters for his model, having interaction visualization of a fitting line or whatever you can think of is always better. If there's no point and adding the interaction is just a toy, avoid it.
Yeah, so if there is no other question, we can thank our Giuseppe for this talk.